I'm going to share with you a bit of the work that we've been doing on efficient computing at the intersection of kind of hardware and AI and robotics. Of course, I'm going to present quite a bit of work, and it's all done in collaborations with various other faculty collaborators as well as students within my group. Full list, and various versions of these slides are on the website if you want to take a look at it afterwards. So in general, when you think about AI and robotics, a lot of the computing is happening in the cloud, but there's actually many compelling reasons why you want to move the compute from the cloud to the edge itself where the data is being collected, like into the device. So for example, if you want your applications like AI and robotics to not be so reliant on the communication infrastructure so that it's accessible to people around the world, that's one reason why to kind of untether the compute from the cloud itself. Another reason is when we start thinking about the type of data that we're processing, a lot of that in the financial or in the healthcare space, for that type of data, there's a lot of privacy or security kind of sensitivities to the data. And so you might not feel comfortable about streaming that data to the cloud itself. So again, you might want to bring the compute from the cloud to the edge or to the data that's being collected, right, to minimize the communication of that sensitive data. And then finally, if you think about applications where you interact with the real world, so for example, robotics or even things like AR, VR, latency is very critical, right? So you might not have the time to send the data to the cloud. So for example, if your car is going very quickly down the highway, there's an obstacle, you might not have time to stream the data to the cloud, wait for it to be processed and come back, right? So again, you want to bring the compute into the robot itself. So for all these reasons, it's really desirable to move the compute to the edge. But the challenge for doing that is actually going to be the computing cost, right? So early on, we're building prototypes for things like self-driving cars. These cars collect 6 gigabytes of data every 30 seconds. And so just the power that's consumed for crunching the data and just processing the data itself, you're talking about over 2,000 watts of power consumption. And so as a result, it generates a lot of heat. And often, that could make sitting in that vehicle uncomfortable. It also takes a lot of space, and you often need to have, water cooling as well. This is what kind of motivates one of the big challenges, which we will address.
Many of these people are running 40 GPUs at watts.
Correct. That's a huge amount of power. I should put in another slide here. I think, last year people also showed that the carbon footprint of a lot of the compute is pretty ridiculous, especially for machine learning. Relative to, it was orders of magnitude high. To do a neural architecture search for a transformer is, orders of magnitude higher footprint than like a flight across the US or even like the lifetime of a vehicle itself. So that's something to think about, right? We're all concerned with climate change, and it's actually having a substantial footprint, the compute, just in the cloud itself. And then let alone if you want to move it out into an embedded device. So this is, one challenge for a vehicle itself, and, this is why we're going to talk about specialized hardware. Tesla's moving towards specialized hardware. This is one of the reasons. The other thing is this is for a vehicle, but you can imagine that these challenges will become even more concerning when you shrink down the form factor of the robot itself. So you think about a small robot or maybe something that can fit in the palm of your hand, like your phone. This is also going to be a big challenge. In particular, for these kind of portable or battery-operated devices, the size, weight, and cost of battery is limited. So the amount of energy that you have is very limited. And then also, if you look at existing embedded processors for the edge, they tend to consume, over 10 watts, which is an order of magnitude higher than the typical power budget you would have for these edge devices. You can imagine that for something that you're holding or you're going to wear, the power consumption is typically limited to under a watt, and that's because you don't want it to create too much heat. Right? You're going to be very sensitive to the heat generation. So in the past, one way that people got around this was basically we waited for Moore's law and Dennard scaling to give you faster, smaller, and more efficient transistors. But we know that over the past couple of years, that trend has been slowing down. So you just can't rely on having these better transistors. And so really, one way that people have turned towards tackling this issue is you need specialized hardware. It can give you significant improvements in speed and energy efficiency, particularly the efficiencies that you need to do these emerging applications like AI and robotics. In order to achieve this, you really need to think about redesigning the computing hardware from the ground up. And this is really the theme of, the Turing talk in 2018. So Dave Patterson and John Hennessy won the Turing Award, and this was their main focus, like how do you build domain-specific hardware. So that's one thing. I think in general, though, taking a step back, we really need to think across the entire computing stack. Now, not just the hardware, but also starting with algorithms. So like, you guys design a lot of models here. Obviously, one driving factor right now to design these machine learning algorithms is just to improve their accuracy. And that's really important. But at the same time, it's important to start thinking about how to make them also more efficient for computing as a kind of a joint optimization. The other thing is, as I mentioned, start thinking about designing new hardwares. What could that mean? It means from like a computer architecture standpoint, where do you put the memory? How do you divide up the memory? How do you distribute, for example, the memory across the different computing engines that are performing, the multiplies and accumulates? How do you build, dedicated chips to demonstrate these compute architectures? And then finally, for some applications, what you care about is not just the compute, but how it integrates into the actual system itself, right? So if you think about things like a robot, the key idea here is that you want to minimize the overall power of the robot itself. So it means looking at, the trade-offs between computing, actuation, sensing, and so on. Okay, so really taking a whole system-wide approach, across different layers to address energy efficiency or efficient computing because the transistors are not becoming more efficient. So if we're going to do this, the first thing you should always ask is, so where is the power actually going so that we can actually start tackling this? And it turns out that the power is dominated by data movement. What we mean by this is that, for example, to do operations like multiplies and adds at different precisions, they might consume a certain amount of energy, as shown here. But actually moving the data, so bringing in the inputs to the multiply and then moving the result of the multiplier back to the memory actually consumes more power. So for example, if you're reading from an 8 kilobyte memory on your chip itself, on your computer, which is very small, you're going to consume 5 picojoules of power, of energy, whereas that's already going to be more than a 32-bit floating point multiplier, right? And then, of course, if you're going to read that data from off-chip, like outside of the computer chip itself, you're talking about orders of magnitude higher energy consumption. Just keep in mind, this is on a log scale, so this is like quite extreme.
Can I read that as compute is free?
Yeah, you can say that compute is much cheaper than data movement. Yeah, I would say that you should tackle data movement first. And so, I mean, the main takeaway here is that, memory access or data movement is orders of magnitude higher energy consumption than the compute itself. Okay, and so this is obviously going to be a challenge when you start thinking about these exciting applications that we're talking about. So if you think about autonomous navigation, for instance, it uses a lot of data. So one of the first things that you do in the perception aspect of it is you want to do some things like semantic understandings. That means that understanding what each pixel means, that this pixel belongs to the ground, and this is the person, and these pixels belong to the sky. Typically, you want to be able to do this at high frame rates, especially if your vehicle is moving very quickly because the scene around you is changing. You might want to do large resolutions so you can see objects that are, very far away. And so just, regular actually resolutions like HD images, you're talking about 2 million pixels per frame. And then often if you want to be able to detect objects of different scales, for instance, you might have to do some data expansion, for example, build a pyramid. And that's going to increase the amount of pixels, the amount of data you should process by another 1 to 2 orders of magnitude. Another form of data that we use in autonomous navigation is geometric understanding. So as you're navigating the world, you're trying to build a map, figure out where the obstacles are, and you can imagine the size of the map is going to grow as you navigate more and more. Right, so that's one challenge. Another challenge is, again, understanding the environment, doing things like depth estimation, right? So, if you have given an RGB image, can you predict, where the location of the pixel is in a kind of a depth position, semantic segmentation where we talked about it. So for these type of applications, we know that, techniques that give us state-of-the-art accuracy basically revolve around deep learning, right? These days, deep learning gives state-of-the-art accuracy on, a variety of perception tasks, but they often require up to several hundred millions, if not billions, of operations and weights for the computation itself. And if we compare this to something that you all have in your phones, which is video compression, right, until I just watch videos or do FaceTime, we're talking about, 2 to 3 orders of magnitude increase in complexity for deep learning per pixel. So, if the goal is to make something like deep learning as ubiquitous as something like video compression so that everyone can have it on their phone. This is quite a gap that we need to close in terms of complexity to make that happen. But even if it's super accurate, this is going to be an issue that we face. Again, I don't think I have to say too much. Beyond perception, deep learning is also used for a wide range of AI tasks. Given this audience, I think I can move on. But in general, we know that it's important for a wide range of things. So if we take a closer look at deep learning and looking at the kind of processing that's happening for deep learning, there's actually several properties that we can leverage that are very friendly towards computing. So the first thing is high parallelism, right? So we know that deep learning is basically a bunch of multiplies and accumulates, and many of those, particularly the ones that happen within a layer, can happen all in parallel. So high throughput or high speed is possible. This is also why it's very well matched to things like GPUs that have a lot of parallel processing. The main challenge, it should be no surprise, is the memory access, which is the key bottleneck. Just to give you guys an idea, right? So if you do a MAC, a multiply and accumulate, for every multiply and accumulate operation, you need to do 4 memory accesses. Right, so you need to read the filter weight, the image pixel or the feature map activation, the partial sum, and then you need to write out or update the partial sum. So that's a 4-to-1 ratio already. If you take a look at the energy consumption for each of these, in the very worst case, you would read these from, let's say, an off-chip DRAM memory. You really try to never do this, but this would be 200x the energy per read, right, or per write, and then again, it's a 4-to-1 ratio. So for something like pretty old, but AlexNet is the 700 million max. You're talking about 3 billion DRAM reads. For more advanced things like resonance, the same thing. The ratio is still the same, 4-to-1. There are some other properties in the neural nets that we can use to exploit, in particular what we call data or input data reuse opportunities. Right. So for instance, basically what this means is that in some cases we move the same piece of data to the hardware itself. We move it once, but we can use it for many, many operations. Okay. So for those of you who are familiar with convolutional neural nets, obviously when you think about convolution, we're actually reusing the same pixels and weight information just in different combinations. So we call this convolutional reuse. In many cases, when you apply multiple filters to a feature map or image to generate multiple output channels, that means that each pixel in the image is going to be reused multiple times across the different filters. Right? So you can use once you read one pixel, you can use it many times for many different operations. And then finally, if you're going to process a batch of input data, right, then means each weight in the filter, you can reuse it multiple times across the different sets of inputs or different feature maps. Okay, and so the key idea here is that there's all these input data reuse opportunities. So how can we exploit this? So we can use what we call specialized hardware. And the idea here is that you build hardware that has very low-cost memories. And what do we mean by low-cost memories? We mean basically memories that are very small, so under a kilobyte in size, and they're located really close to the compute unit itself, right? So for example, you have a multiply and accumulate here. You might have a local register file that's under a kbyte. It has some local control. We typically call this a processing element or a PE, and then you might have an array of these, which then talk to a shared memory and then talks to DRAM. Right, and so reading from, if doing a multiply and accumulate is 1x, reading from this very small memory that's under a kbyte of memory is going to be also 1x in terms of energy. Reading from a neighboring processing element is going to be 2x in energy. Reading from a global buffer shared memory is going to be 6x the energy, and then DRAM is going to be most expensive. And so the idea here is that, farther and larger memories consume more power, and ideally you'd like to keep on reading as much as possible your data from this small memory. So I know, to give an analogy here for those who don't have as much of a hardware background, I think it's very much similar to if you had to do some work, getting data from your backpack or your bag is going to be much cheaper. You can think of what that is, like register file. You could borrow information from your neighbors, or you could let's say go back to your desk. That's a little bit more work. It's a shared area, or you can go back to your apartment or home. That's going to be much more expensive, but you have much more space. You can store many more things there. Right, so the idea is you can only store so much, very limited amount in your backpack, but it's very cheap to access it. So what should be the data that you're storing there so you can get the most amount of work done? That's basically the question. And then if you can coordinate with your colleagues, what should they be storing so you can exchange data and get the most amount of work done without having to move the data around too much. Okay.
You know how these ratios scale with Moore's law?
Yeah, it's a great question. So this is an example with 65 nanometer process technology. So certainly these, the absolute numbers will change with Moore's law as the transistors get smaller, but in general, the ratios really what's dictating the energy is the capacitance of the wire, right? So the reason why smaller memories are cheaper is because they use less capacitance and they're closer by, so you're switching less capacitance, versus when they're farther away, you're going to switch more capacitance. So the same concept will hold as a fundamental physics aspect. Yeah. Yes.
Should you figure out how much energy to save doing this? What do you think?
Yeah, so I'll talk about it. You're talking, you can do depending on how you. So first of all, there's various aspects of the hardware. One is to like specialize and get rid of all unnecessary stuff that can help you a lot, and then this can give you like another 2x of energy, because this is one way you can optimize more, like specialized hardwares that optimize for this. If they're all optimized in different ways, I'll talk about it's like around 2x, but if you compare to really poor baseline, you can be like 10x. Depends on. Yeah, so I'll give you some. So for example, we'll show that we built like specialized chip that consumes under a third of a watt, right? That can do this kind of stuff. But is the concept clear in terms of what we're trying to do here? Just trying to, and so the big challenge here is that neural nets is a lot of compute, and so how do you decide how to take a large neural network and chop it up into pieces and put it in these small memories, and then what is the right order at which you should process each of the chunks so you can maximize the reuse? Okay. So there's been a huge amount of research in this space, and so what we did within our group was kind of classify each of them and to describe them. So one approach is the weight stationary approach. And so the idea here is that the weight itself is going to be stored in that local memory. And then as a result, what moves around is the pixel information, the partial sums. So this is widely used. These are a range of publications, but I should also mention this is used for TPU and NVDLA, right? So GPU is from Google, and then NVDLA is a custom accelerator from NVIDIA. So this is the kind of this is what we call the Dataflow that they use. So they hold the weight station, try to minimize the energy of the weight itself. Another approach is the output stationary approach, and the idea here is as follows. Well, weight you only just read once, but partial sum you have to read it and then update it and then write it back. Right, so there's two memory accesses for the partial sum. So maybe it's better to keep the partial sums local in the register file itself, or basically the output, the accumulation of the output stays the same within a processing element in the register file itself. A third approach, which is something we did within our group, is kind of looking more at, rather than focusing on one particular data type, why don't we try and minimize the data movement or maximize the reuse across all data types. So the idea here is within a processing element, what you'd actually do is try and process one row of a DNN locally inside. And so this allows you to exploit convolutional reuse between the filter and the feature map. So we also color code these things. So filter is usually green and then feature map is blue. So you can see you do one deconvolution there. And then you also can maximize the partial sum accumulation for those. And then you can imagine you can stack many of these together, each of these together. So you're doing 1D convolutions in each of the PEs, and then you're doing vertical accumulation of the partial sums. You're reusing data there, so you're not going to global buffer, you're sharing between neighbors. You can also see that the filter information is repeated across the array. So if I read once from that global buffer, it's like, let's say I go once to your desk to grab data, then I share them across multiple processing elements. So it's like equivalent to sharing them to many of the colleagues here. So you can see there's a lot of repeated data here, so read once and reuse it multiple times. And similarly for the blue part or the input part, you can reuse diagonally. Again, if you're interested, I recommend checking out the IRIS paper. But the main takeaway here at the very highest level is that rather than focusing on minimizing the data movement or exploiting reuse for one particular data type, what we're trying to do here is optimize for overall energy efficiency. And so trying to balance the reuse across the various different data types, right? So just to show, if you use kind of optimized hardware for each of these different approaches, you have the weight stationary one where the weight doesn't move. You can see here, this is the energy consumption. So the weight, the green part, has the minimum amount of energy, but it comes at a cost of that the partial sums shown here in the red and the pixels shown here in the blue are moving around a lot. Alternatively, you have the output stationary approach where we said that the red part, the partial sum, stays stationary. And you can see here that the red part is the lowest. And then the green part, the weights and the pixels are moving around, and there's 3 variations of that. I don't have time to talk about no local reuse because it's not good. Whereas row stationary, since we're trying to minimize the overall energy consumption, you can see that, for example, the partial sums is larger than output stationary, the weights is larger than the weight stationary. But when you bring it all together, you get an energy efficiency. right? So it's in some sense, it's not a surprise. You're thinking, if I optimize overall as opposed to like focusing on one particular data type, I should do better.
You were writing Python code. Can you influence this?
If you're writing Python code, can you influence this? I think your compiler, your hardware has to support this, and then your compiler has to map that to your hardware. So this is more about kind of how do you design the hardware from the ground up. So another thing that you can easily do is exploit sparsity as well. This is kind of a side note. So we know that anything times 0 is going to be 0. We also know that in neural nets, we have a ReLU that basically sets all negative values to 0. So there's a lot of zeros. And so what we're saying here is that if you can recognize zeros, you can basically skip the memory access and the computation, and you can drop the power consumption by 45%. You could also apply things like compression, right? You have a bunch of zeros, you apply like very lightweight run length coding, and you can drop the amount of data movement by 2x, and of course, or storage cost data movement by 2x, and of course that's important because data movement is expensive. So what does this all result in? So this is the Iris chip that we published back in 2016, basically demonstrating all these concepts. First of all, the rotationary data flow. So it has 168 processing elements, has a 100K shared buffer, and then has some compression before it goes off to DRAM. And this is a diphode itself. It's 4 millimeters for 4 millimeters. But the main idea here is that because of that rotationary data flow, we reduce the amount of memory access from this global buffer. Again, in that analogy, it would have been like your desk by 100x. And then we reduce the amount of data movement from your off-chip memory by over 1,000x. Right? Again, because most of the time the data is being fetched from that local memory or being shared between the neighbors. And so when you compare it to an embedded processor like NVIDIA's TK1, you're talking about order of magnitude reduction in energy. Yes.
So does it include also data compression or not?
This includes some data compression as well.
And then does it affect like the accuracy? If you compare it
No, so it's going to be lossless data compression because basically when you have a bunch of zeros, you can do what we call run length coding rather than symmetry. Of course you can, there's been a lot of research of people applying things like quantization and stuff on top of like lossy types of features, and then that'll sacrifice some accuracy. But even like for this, if we take a step back at the highest level, so let's say I don't really care about hardware at all, I just care about the system, and I want to basically, what I care about is actually the trade-off between energy and accuracy, right, at the end of the day. Like, I don't care how you guys built it or whatever you guys did. And we look at this for an object detection problem. So on the x-axis here, where it's on the linear scale, it is measured in average precision, so higher is better. And on the y-axis, we have the energy consumption measured in energy per pixel. So right off the bat, if we compare HOG, like histogram-oriented gradients, which is a handcrafted approach, which I would argue was popular right before all the neural net stuff returned to popularity, you'll see the accuracy's okay, not that great, and then why people are super excited back then about like Alex and VGG is because he basically doubled or almost tripled the accuracy itself. So that's on the accuracy scale. But then if you look on the energy scale, the story is quite different. So in particular, I just want to mention these energies are actually measured from specialized hardware, both for the HOG chip as well as for the Iris chip that we just talked about to do neural net processing. And what you'll notice is a substantial increase in the energy consumption. And as a reference, video compression is typically around 1 nanojoule per pixel. So what's interesting is with HOG-based features, you can actually, the energy required to understand the video can be actually less than the energy required to compress the video. So you could imagine using HOG-based features that you could be as ubiquitous as video compression. You can imagine like every sensor would have this recognition behind it, but it's not as accurate. If you move to something like Alex and or VGG, the energy consumption grows exponentially. You're talking about 300 to 10,000x increase in energy consumption, right? And so I think the way to think about this is, who here would be interested in doubling the accuracy for 300x decrease in the battery life of their phone, right? Or tripling the accuracy, but your battery life is going to die 10,000 times faster. Right? This is so obviously energy, the point I'm trying to make here is energy is a very important component of actually being able to deploy these things. Yes?
You mentioned specialized hardware. How easy is it? How well can you predict the actual energy use? I just something pops.
That is an excellent question. So I'm going to talk about that in maybe like 3 slides. And I think that's a fundamental problem in the space because folks are, yes, trying to count ops and trying to count weights and using that to predict energy and latency, but it doesn't match up exactly very well. So understanding hardware is really important. Any questions about this? At least the motivation as to why energy is important. Even if you have spectacular accuracy, groundbreaking, I mean, you yourselves would not be willing to take, or I don't know if anybody would be willing to take, allow their phone battery to die 10,000 times for triple the accuracy. You are super interested in that technology.
Problem is that accuracy thresholds sometimes make or break a technique, right?
Understood, but sometimes also battery life makes or break a technique too, right? That's why I want to emphasize, often, I'll tell you another way to look at it. Often, in machine learning conferences, we really focus on this, and on hardware conferences, or systems conferences, really focus on this. And I think really, if you want to think about solutions in this space, you need to think about both. Right? So actually, there's been so one goal that you would like to do is actually maintain the accuracy, just reduce the energy consumption. And actually, it turns out there's a huge amount of research in this space over the past few years because of the popularity of GNNs. So we actually, in my own group at MIT, we spent quite a significant amount of time looking and surveying the different algorithm and hardware research techniques that do this. In fact, we produced a bunch of tutorial material on this, both in terms of tutorials at conferences and a big survey paper on this. So if you're interested, I would invite you to take a look at this. But what's been interesting is by doing this kind of a survey, we actually identified various limitations of these existing approaches. And that leads towards your question in terms of how things like number of max and weights affect actual performance. So in many of these, if we go from the algorithm side, many popular efficient DNN algorithm approaches really focus on things like network pruning, so setting more weights to zero, or using more compact network architecture. So if you're familiar with MobileNet or SqueezeNet, using stepwise decomposition and so on, reducing the number of ops there. And of course, reduce precision. Rather than using 32-bit float, can you use 16-bit or 8-bit or even below that? And so a lot of this work focuses on reducing the number of max and weights. But again, if you think from a systems level point of view, if you're trying to look at the overall system, does this actually translate into the metrics that we care about, which is saving energy or reducing latency? Right? So latency is reaction times. It's really important. So if you think back about a slide that we just talked about, data movement is expensive. We can see that, for example, the energy of the weight can vary. It can really depend. It really depends on the memory hierarchy. So where does the weight come from? Does it come from this register file? Does it come from this buffer? That makes a big difference. So all the weights in the neural net are not created equal. It really depends on how it's mapped onto the hardware. So the memory hierarchy and the data flow really matter itself. So in summary, you can't just count the number of weights and be like, okay, this is how much energy it's going to consume, because it really depends on, can you reuse that weight many times and so on, and where it's actually stored. So one way to do this was, within our group, we started to build these energy evaluation tools so that basically you can put in a DNN shape, also show the sparsity of the DNN itself, and then it would actually do this memory access optimization and kind of give you a breakdown of where the energy is actually going based on the memory hierarchy and the number of max, and for example, which layers consume how much energy. And this is available on Energy Estimation website. And one of the key observations, which should not be a surprise to you guys, is that the number of weights alone is not a good metric for energy. For instance, all types of data should be considered because we're thinking about data movement, right? And so weights only actually, if you look at GoogleNet, weights only account for 22% of the energy. We also have a lot of data that's moved for the input and output feature maps as well, right? So that should also be accounted for. And again, also where the data is moving from also matters, and how much is reused also matters itself, right? And so then the next question we had within our group is, once we knew this, could we kind of augment or change the approaches that people were taking to make these nets more efficient to include this type of information? So in particular, can we design algorithms that directly target energy during the optimization of, let's say, the DNN itself? So one example of this is looking at the task of pruning. So again, remember, pruning is basically removing weights and basically setting them to zero. So, at the same accuracy, if the original unpruned net, consumed an X amount of powers, you doing magnitude-based pruning, which is the typical approach, is removing weights that are small with low magnitudes, you could basically half the energy consumption. But again, there's no reason why you should be removing the small weights. In fact, you should think of removing weights that consume the most energy. So one approach that we took was we decide to sort the layers of the neural net based on the energy consumption, and then prune the layers that consume the most energy first. And the reason for that is we know that typically as you remove more and more weights, your accuracy is going to drop. So you basically want to try and remove the high energy weights first to try and get a better trade-off between energy and accuracy. And so by doing this, you can actually drop the energy consumption by about 3.7x. Right? And this is just one example of, if you really factored in energy into the design of the algorithm itself directly, as opposed to using weights, which might be a proxy for energy, you can get much more efficient results. Yes?
What's the
What is the... The intuition. Okay, so the reason why, I guess there's two ways to answer. So one is that, why do some layers have more energy consumption than others? Is that your question? Yeah, so some layers just naturally have more data movement than others. And so it's going to cause more energy consumption. So it depends on where the weight is read and how often it's going to be read. So if, let's say there's a weight that has a lot of reuse, then it might have less energy consumption, more energy consumption than others, right? So you can if you remove that weight, you're going to overall save more energy, right?
Well, why does that get
So it depends, right? So there is going to be a breakup point with how often they actually use it. Sure, if it's just removing it once and reading it twice, maybe there's not going to be that energy costly. But if you use it many times and you remove that, then you could be less. And it's just to take all of that into consideration as opposed to just counting the weights. Right? Yeah. So this is one tool that we designed for our particular hardware that can do that. You could imagine also doing things like computing weight reuse for specific hardware.
But the problem you were saying earlier is that this is tied to the actual design of the hardware and the compiler language.
Yeah, so I think I would say by no means that this is, actually I'll show you soon another one that you can use if you don't have actual modeling of the hardware. So this particular approach this is the first kind of paper that we wrote that was looking at incorporating this stuff in. We, drove this using energy from Iris, which is the custom accelerator. In 2 slides from now, I'm going to talk about an approach called NetAdapt, which we developed in conjunction with Google, and that's just basically taking empirical measurements from hardware. So it can be any hardware, and then use that to drive. But the main message here is that, if you're trying to minimize energy or minimize latency, you should bring that into your algorithm design as opposed to just looking at number of weights and number of mass, which is easy to count, but it could lead you in the wrong direction. You had a question?
So it is based on your
This is driven by this energy estimation tool. Okay, so I hope the take-home message for this is clear, that you want to incorporate that information in. Another thing that you might care about is latency. And often people think latency and number of operations are associated with each other. And so this is from the blog post from the Google mobile team. And they were showing that this is indeed not the case. So for example, if you look at the number of max or operations here, so horizontal, and then latency vertically, you can see that, in some cases where you have the same number of operations, you can have a 2x swing in terms of latency. And in this case, the same latency can have a 3x swing in terms of number of max. Right, so that means that number of max is not necessarily a good predictor of latency. Okay. And so, again, inspired by the energy-aware pruning work, we worked together with them in terms of figuring out, how could you basically do this in a more automated way? Let's say you don't have information about all the different platforms itself. Can we just take the platform and empirically integrate it into the design of the neural net? So together we did this work called NetAdapt. So it's a platform-aware DNN adaptation module. You can think of it as a form of NAS maybe, but basically you start with a pre-trained network, and then you have a budget, for example, latency or energy consumption, or a combination of both. And what this NetAdapt does is it generates a bunch of network proposals where, for example, it will modify the network in a little bit in various different ways. I'll explain what it is later on. And then you can measure the performance of these networks on an actual embedded device. So for example, their energy or latency, and then you can feed that back into the net algorithm. And so basically what's happening is that this pre-trained network is going to be adapted to the performance of that particular platform. It's all in an automated way. So you can imagine for places like Google, they have a whole bunch of platforms, new platforms come in, with the new OS, new like software stack, new hardware, and so they can just automatically basically adapt a given network for ideal performance on that particular platform. So one simplified way of how you could do this is as follows. You can start out with an input. Let's say you have a pre-trained network at an accuracy that you like. The latency of that network is 100 milliseconds, but your budget is 80 milliseconds, right? So what you can do is you can generate a bunch of proposals where a simple proposal would be that I would, for each layer, reduce the number of channels until I hit that target budget, right? So let's say 4 layers, you have 4 proposals. Then you look at the accuracy of each of these proposals. You pick the one with the highest accuracy, right? You might do some fine tuning, and then basically you move on to the next iteration. The next iteration, you would further tighten your budget and so on. And then you can imagine by doing this, what ends up happening is that you generate a series of efficient DNN models. So on the x-axis here, it's latency. On the y-axis is accuracy, so higher to the left is better. And so NetAdapt is generating a series of these models, which are gradually becoming more efficient. And you can see compared to using kind of handcrafted approaches to kind of just size the model based on the number of operations, you can achieve 1.7x faster at the same accuracy. Okay. Again, I'm not saying that this is the ultimate way of doing it, but again, the key message here is this is a way that you can incorporate things like latency and energy directly into the design of the neural net. Another thing I want to point out, so this is on this is on the smallest mobile net that we showed this on. So again, we all know it's easy to take like a large AlexNet and then make it smaller, but we also want to showcase that even on a small network, we can further improve its efficiency with this particular approach. Nonetheless, this is still on the task of image classification. So what we wanted to ask next is, would it work on a more complicated task? For example, depth estimation. So in classification, you're typically reducing the information, right? You have a set of pixels, you're reducing to one label, and you can imagine it might be easy to kind of reduce the complexity of that net. Whereas if you think about applications like depth estimation, where you have a dense output, where basically every pixel in the image has a label of depth, it might be harder to make that network more efficient because the requirements for it are much more stringent. And so for those of you who are not familiar, monocular depth estimation is basically I give you an RGB image and you're going to predict the depth of each of those pixels. And the motivation for this is because it's lower cost, right? Rather than having a depth sensor or an active sensor on your system, you can just use regular RGB camera. Typical architecture for this type of application would be like an autoencoder. So you have to start with an encoder layers, which are basically your classification, then you would expand the data with your decoder itself. And so basically, we applied NetAdapt to this as well as some other design strategies, and we're able to show that indeed it still works on these types of tasks, not just for image classification. So these are some measured results on a Jetson TX2 embedded GPU in terms of frames per second. On the horizontal axis and on the vertical axis, it's the accuracy in terms of delta 1, which is basically the percentage of pixels which are within 25% of the correct depth, right? And so you can see that for approximately the same accuracy, you're talking about a 10x speed up. We actually presented this at ICRA last year, so we also captured some live video there at the ICRA conference itself. And on an iPhone, for example, could run at 40 frames per second. So this is, again, primarily to show, this fast step was to show basically that the techniques that we apply to classification still hold for a more challenging task of depth estimation. And so all the code and models on the FastDepth website. So that's all on the algorithm side of things. Again, the big takeaway from the algorithm side of things is you should bring hardware into the loop when you're designing your algorithms. On the hardware side of things, it also presents a lot of interesting challenges. So again, people are designing new algorithms like network pruning, compact architectures that reduce precision. From a hardware designer's point of view, the challenge is that there's no guarantee as to which technique an algorithm person is going to use, or model designer is going to use. And so as a result, this forces your hardware to be much more flexible, or needs to be much more flexible if you want to support all these new techniques. And so this has been a challenge in terms of designing specialized hardware. We said we want specialization for it to be more efficient, but now you also need it to be more flexible in order to support all these techniques. One of the challenges when you think about specialized hardware like TPUs and NVIDIA is they often rely on certain properties of the DNN in order to achieve high efficiency. A typical thing that you want to do is you have an array of multiply and accumulate units, and you want to read one piece of data from, let's say, the weight, and then reuse it multiple times horizontally, or read an activation input and reuse it vertically a lot. But the challenge here is that the amount of reuse that you can get across the array depends on the number of channels and the size of the feature map and batch size, right? And this can be an issue when it's okay when you have these huge networks that have a lot of reuse and a large number of channels, large feature map, and so on, but it's not going to be efficient across all network architectures, particularly these compact DNNs. So you think about things like MobileNet, right? We have these layers that are called depthwise layers that only have one channel. And so as a result, when you have these array of MACs, only a small subset of it is actually going to be able to be used to process this MobileNet itself. And this is the reason why just because your network is smaller doesn't mean it's going to run faster, because if it doesn't map well onto the hardware, it can't use all the parallel processing engine. This is also going to be an issue as you scale up the size of your array, right? It's going to have lower utilization. And then if you have sparsity, like a bunch of zeros, it's actually very hard to exploit. So what you need is actually very flexible hardware. One thing is to have a very flexible data flow in terms of how the data can move through the system. So if you have spatial accumulation, which is weight stationary, temporal accumulation, which is output stationary, again, you're very limited in terms of number of PEs that can operate. With a more flexible data flow like row stationary, you can fully utilize your PEs. Another thing that you really care about is how you deliver the data. And so in terms of delivering the data from your memory to your processing elements, there's a range of approaches you can take. So on the most extreme side is low bandwidth, high spatial reuse. So if I'm like the global buffer and I'm delivering information to all of you guys, if you guys are all able to take the same piece of information, I can basically broadcast the information, or multicast it. Basically, this is low bandwidth because I'm sending very little data, but it's high spatial reuse. A lot of spatially, you guys are using it all at the same time. And so this is very good, again, when you have these very large neural networks that have a lot of reuse. But at the other extreme, again, we have these very compact neural networks, like MobileNet, where there's not a lot of reuse. In those cases, what you need is on the left-hand side here, high bandwidth and low spatial reuse, which means that I would need to give you guys each unique information, right? Because I can't reuse the data. And this is really important for things like, as I mentioned, like the more compact layers, but also like the fully connected layers. And so, again, since you want to be able to run any type of network on your hardware, ideally you need to span this whole space. But that's going to be really challenging. A typical solution would be an all-to-all network, which you can imagine is very, very expensive and not scalable. So one approach that we took within our group is to build what we call a hierarchical mesh. So we kind of break it up into two steps. At the very low level, you have these clusters of processing elements that do all-to-all data sharing. And at the higher level, you do kind of a mesh connection that allows you to scale. And with this, you can basically have various forms of data distribution. Again, the main takeaway from this is that was kind of a key component in the second version of Iris. And then the real thing is trying to basically balance flexibility and efficiency together, right? So as a result, when you have a much more flexible on-chip network, you can support a wider range of filter shapes, both large neural nets and more compact neural nets or layers like depthwise layers. And so with this, you can imagine you're getting like an order of magnitude speed up. You can also support a wider range of sparsity. We didn't talk too much about this, but you can design hardware that identifies zeros, but there's going to be overhead to do that. Right? So you don't want that overhead to be too much because someone could also just give you a very dense network without many zeros, and you still want to be efficient for that. This is a very scalable architecture, so increase the number of PEs. You can see that the speed up, there's also a speed up that you can see. So when you compare it to the first version of Iris, that doesn't take all of the wide range of DNNs into account. You're talking about an order of magnitude speed up and order of improvement in energy efficiency. All right, so I'm going to skip this next one. Just very briefly, maybe, the major takeaway here is that there's actually a huge amount of work designing DNN hardware. And so one thing that we've been doing within our group is to develop tools that allow us to quickly assess at the very early stages of design in terms of the efficiency of the hardware itself. So if that's something you're interested in, I would invite you to visit the Accelergy website. But the idea here is that because there's many ways to design DNN hardware, but it takes a lot of time to design hardware, the earlier you can figure out how efficient the hardware is, the better, and then you can explore the space much more. So you can imagine it's also like a search space of your neural nets. And then this tool that we developed showed that you can get like 95% accuracy. All right, so that's all I want to say about DNN. And then just very briefly, I just want to talk about some other projects that we're looking at within our group. Perception is fine with DNNs, but actually the task of localization is actually still a non-DNN based approach, particularly what we call visual inertial localization or odometry. And the idea here is that you basically want to know where before you can do autonomous navigation, you need to know where you are and where you're looking. Right, and so you can imagine, for example, you can do this by mounting a camera on the robot or vehicle and also having an IMU on the robot or vehicle and fusing this information together. This would be a subset of SLAM, if you're familiar with that. And so you can see here, basically, with this drone that's flying around, but doing localization, you're basically, figuring out where it is in the 3D space. And if you're flying around an unknown environment, you might also want to build a 3D map of your environment as well. So that's one of the big focuses of the research within our group. And so what we wanted to show is that we could do this in a very efficient way. So we actually built a chip called Navion that can do localization in under 25 milliwatts. Right? So this is the first chip that can perform the complete visual inertial odometry pipeline. It has the front end for the camera, so it's doing things like feature detection, tracking, and outlier elimination. It also does some pre-integration for the IMU. And then the back end, it does a post-graph optimization to fuse that information together from the different modalities. So here's the chip itself. It's 4 millimeters by 5 millimeters. You can see it's smaller than the size of a quarter. You can imagine mounting it on these small drones. And when you compare it to a mobile or desktop CPU, you're talking about hundreds, if not thousands of X more energy efficiency. And in fact, at 24 milliwatts, it can still hit up to 171 frames per second. So this is useful for navigation. It's also useful for AR, VR. So in fact, the student who worked on this is now working at Facebook for their AR, VR division. Now, how can we actually achieve this? It actually focuses on memory. Again, it's the same theme. So the key idea is that we want to integrate everything, all the processing on chip, because we know that moving data on and off chip is very expensive. So you want to integrate everything on chip, but then if you're going to put everything on chip, you don't want to have a humongous chip because that's also expensive. So on the chip itself, we also apply low-cost frame compression, as well as exploit sparsity. And so all in all, for all of this processing, we can do it with under a megabyte of on-chip memory itself. Okay. Skip the next thing. So one last thing that we've been looking at in our group is more in the healthcare space. So we know that neurodegenerative diseases like Alzheimer's and Parkinson's affects 50 million people worldwide and continues to grow. So they're expected to hit 75 million people in 10 years. The big challenge with this is that the neurological assessments for these type of diseases are very time-consuming and they often require a trained specialist, right? So you need to go into the clinic and they might ask you a series of questions and they might also ask you to do some tests like drawing a clock. And so because it's very time-consuming and expensive, people typically do it very infrequently, right? So they might do these tests maybe once or twice a year at the most. So you get very sparse measurements. They're also very qualitative, so depending on which specialist you go to, you might get a different assessment. And so there's also high retest variability. What's been super interesting is that there's been research that shows that basically eye movements can give a quantitative evaluation for these particular diseases. So it can be used to basically evaluate the severity of the disease or the progression or regression of the disease, depending on like if you're taking some drugs, is it working or not. And so it's complementary to the specialist, but nonetheless it's useful to have. But the challenge for this right now is in order to do these, you still need to use very fancy equipment. Right? So you need high-speed cameras, you often need to restrict the head with substantial head support, or you need IR illumination. So again, this forces the person to go into the clinic to do these type of measurements themselves, to measure things like saccade latency, which is basically eye reaction time. So that's to be done in a constrained environment. So what we've been looking at, this in collaboration with Thomas Helt in the Institute of Medical Engineering and Sciences, is to look at whether or not we can replicate these tests and put them onto the phone itself or a tablet itself. And so then as a result, you can imagine you can repeat these tests many times at home and collect a wide amount of data, which you can then bring into the physician. And so we want it to be also very low cost, so you don't have to use these very expensive cameras, and so it's accessible to everybody. And in fact, we're able to show that, yes, you can already replicate some of the measurements itself. So for example, you can compare like an iPhone 6 to a Phantom camera you can see the same saccade distribution itself. And so right now we're doing age match studies for these, and you can see also a trend in terms of, as you get older, you can actually tell that the eye movement is actually slowing down as well. So you can get all of that resolution just with the camera on your phone or tablet. So that's another one in the healthcare space. We talked a lot about computing, and again, here you can imagine you want to do the processing locally on the device. And actually, Jin did a summer internship with us working on this project. The one last thing is there's computing. There's also sensing that's important, right? So sensing, for example, depth estimation, we just talked about, that's useful for navigation or AR/VR. If you use active sensing, where you just send out a pulse and wait for it to come back, that can be very expensive. That's what's typically done with time-of-flight sensors. What we were been looking at is, can we kind of do an optimization between sensing power and computation itself? So for example, can I turn on the depth sensor at time 0 with an RGB camera, but then turn off the depth sensor at time 1 and time 2, and then use very lightweight computer vision to just estimate the depths here, right? So basically what I'm exploiting here is the temporal correlation across time, as well as the correlation between depth and the 2D image. What's really important here, though, is that the depth estimation, the algorithm to estimate these depths, should also be super light. So in fact, we're able to run it on an embedded processor, like a Cortex-A7, which is a super lightweight processor under half of a watt. And then just to give you an idea of the quality of results, this is what it would look like. So here's an RGB input. If you turn the time-of-flight sensor on all the time, this is what it would look like. If you turned it on every 9th frame, basically 11%, this is what it would look like. And you have a mean relative error of about 0.7%. Okay. So just basically to summarize, let's skip this. Energy efficient AI is really critical to extend the reach of AI beyond the cloud by reducing communication requirements, enabling privacy, and providing low latency. And so it can be used in a wide range of applications like robotics and healthcare that we saw. In order to do this, it's really important to think about cross-layer design, including specialized hardware, to achieve this energy efficiency. It's going to be important for the progress over the next decade. If you're interested more in this topic, we have a couple of resources. One is, again, I would invite you to take a look at this survey paper. It's quite well read, but it just gives you an idea of the overall space. We're also currently writing a book on this, which should be coming out actually next month. And then both the papers and some slides and parts of the book are available on the IRIS website if you're interested in that. Of course, there's updates from our class. And then if you're, so at MIT, we also run 2-day courses on this particular topic. So if you're interested in that, I can invite you to come down to MIT in the summer to take the class. And then finally, we have tons of tutorial material on this particular topic. I know some of you were at the NeurIPS talk, so this is all just available on the tutorial website within our group and stuff. And all of this work could not be done without all the students. Obviously, you guys know students are huge, so they do a lot of the work, as well as collaborators like Joel Emmer, Sir Tesh Kerman, and Thomas Helt, and then the various sponsors. All right, thank you very much.